Perfect. Wonderful. Good morning. Last talk for this morning before coffee. But first of all, I'm Sascha. I'm product manager with DECTRIS, and today it's my pleasure to introduce a new product here at the XRM. It's about Selun, fastest Selun. To make this not a boring vendor talk, I brought a little surprise with me. Today on stage is going to be Darren, principal scientist at I13. And while I'm going to quickly show you what Selun can do technically, Darren really going to show you what it can do for you at the Beamline. So let's start with the first 5 minutes. What is Selun? Selun is a mountain in Switzerland. So are Eiger and Pilatus. You might know us as provider of large area hybrid photon counting detectors, namely the Eiger 2 series and the Pilatus 4 series. It's hybrid photon counting detectors, which means it's no noise detection, it's single photon resolution with high dynamic range and high frame rates, typically over a large area, up to 16 megapixels. Where does Selun fit in here? In there. So Selun is similar, but Selun is quite different. Selun is small and ultra fast. So what Selun can do, it has a frame rate of 120 kilohertz continuous. And continuous meaning that no matter if 1 second or 1 day, the detector delivers 120,000 frames per second continuously with only 100 nanoseconds dead time between frames. Besides fast framing, Selun is also very fast counting. Selun can count up to 45 gigaphotons per square millimeter per second. This gives you a huge dynamic range from a single photon with a huge flux. Besides that, the dynamic range is not affected by the frame rate that you choose. No matter if you record at 1 Hertz or 100 kilohertz, the dynamic range stays the same. Besides that, it's photon counting as you know it from Pilatus or from Eiger. The detector is compatible with different sensor materials to detect at the low energy range and high photon energy range. It's noise-free detection, it's a high spatial resolution, and all of that on a small area of roughly 2 times 2 centimeters. We'll be able to provide the first detectors by spring next year. So, what I want to show you technically is how we actually achieve this frame rate. Because Selun has 2 novel inventions built in. I didn't talk about the pixel size yet. Selun has 100 micrometer pixels. And you can read out the detector with 100 micrometer pixel pitch at 20 kilohertz. You say, I promised 120 kilohertz. In the chip, we have implemented pixel binning. So you can bin 4 pixels to 1 pixel, achieving a 4 times higher frame rate of 80 kilohertz continuously. There's still a bit missing, and that's the next invention in there. It's an on-chip compression scheme that reduces the data bandwidth by 1/3, which means you get another speed boost of a factor of 1.5 to 120 kilohertz. This is going to be my last slide already before I pass to Darren. What can you do with it? So it's an extremely fast detector, an extremely sensitive detector. You can study fast dynamic processes, for example, with XPCS. We did with Yuri at ESRF ID10 some proof of concept measurements, XPCS diffusion of silicon nanoparticles. There we found with 100 kilohertz measurements that you can resolve 8.4 microseconds lag time. Fast framing also goes hand in hand with fast scanning. Yesterday, we heard impressive progress in the method development of ptychography. With such a detector, we did first proof of concept experiments back 2 years ago at the APS with Junjing Den. What you can see here at the bottom is a ptychographic reconstruction with a field of view of 80 times 30 micrometers with a resolution better than 100 nanometers, recorded in less than 1 second. And fast ptychography This is exactly the keyword to pass to Darren because he's pushing that to over 100 kilohertz.
Okay, thank you, Sascha. Hi, everyone. I'm Darren Batey. I'm Principal Scientist at I-13-1, and I've been working a lot with Sascha and Max and the whole DECTRIS team the last couple of years, along with other colleagues at UCL, to really push now the capabilities of ptychography into the high-speed regime. Okay, so I'm going to give you an overview of the beamline quickly, and then walk through some of the steps we've been through in these last couple of years to push ptychography into this 100 kilohertz regime you just heard about. So first of all, I-13-1 is a hard X-ray beamline. It's got a very large coherence length and a large hutch that makes it very, very well suited for all sorts of coherent measurements. Bragg CDI, for example, looking at strain mapping within samples. We can also augment that with XRF for elemental sensitivity, looking at elemental distribution alongside these structures. Methods development as well, so we're very well set up for flexible configurations, looking at new methods going forwards. And our kind of workhorse is ptychographic tomography, looking at nanoscale structures on the tens and hundreds of microns length scales. You will have seen a talk yesterday, perhaps, from Viva. That was one demonstration of this method development, looking at hyperspectral detectors and broadband illumination, and a couple of posters to look out for in the next couple of days as well from CUDA to look at developments more at the beamline. Now, X-ray ptychography, I think you all know fairly well, but just to quickly go over this, you have a small beam on the sample, and you scan your sample through that beam, or that beam through the sample, perhaps now as well, and you record in the far field typically a diffraction pattern, and you can see how this is changing as you're scanning through the beam. When you then invert all of this rich data set together, using algorithms like this, EPI and others, you can then reconstruct this four-dimensional data set back into a single two-dimensional image, which is fully complex, so modulus and phase, at the ultimate resolutions. So ultimate resolution, finite field of view, and the high sensitivity electron density maps. It's the ultimate imaging technique. However, to achieve this, you need to scan a sample through a beam or a beam through a sample, and that gives you overheads in scanning. Typically with X-rays, you have to scan the sample through the beam, and the purest way to do that is a step scan. So you take your sample, for example, a Siemens star, and it walks through the beam like so. But at every step, you have to wait for that sample to come to a rest where you can take a coherent measurement. Okay, so you'd like this to happen in an instant on the left. However, in practice, it takes tens of milliseconds for that stage to actually come to a stable state so you can then start to acquire. And so there is a significant overhead with this approach. So acquisition times are much greater than exposure times in the end. And even with a large beam size, which you can get at I-13-1, and large step size, it still leaves maximum speed in the tens of microns per second regime. It's very, very limiting. So what can we do? Well, continuous scanning was developed a few years ago now, and there what you do instead is move the sample at a continuous velocity through the sample, and acquire frames as you are moving. Now, moving across the area in a continuous motion does remove settle overheads, of course. They go to zero. But the resolution is now limited by the amount of blurring that you have across that time and through that step. And so your blurring is limited by the step size that you can achieve. And that step size is now limited by the detector rate, so how far can you travel in that time. And so in the end, your resolution and your imaging quality now is directly coupled to the detector rate. And so we began playing with the Eiger at the time, and trying to push our existing scanning system to match the Eiger. The Eiger can go continuous 3 kilohertz, P can get 9 kilohertz. Our motion controller could only go at 1 kilohertz. And so we could only control where we were in position at a rate of 1 kilohertz. So we came up with this hybrid triggering system. And it's kind of a combination of a position and a time-based system. So our motion controller can put us into position at a certain rate, and then we can use a trigger box to take this output trigger and to kind of upsample or up-trigger and have a time-based scan in between. And that allows us then to control the position capture and also the frame capture up to 3 kilohertz, even though the underlying motion control is a bit slower. And with the burst mode of Eiger, we also demonstrated that you can actually run a detector faster than your position capture. And with ptychography and a bit of interpolation, you can actually achieve quite a lot by also interpolating in between known positions. And so this whole system then gives you a very flexible way to insert best hardware into different positions and always exploit the maximum capability of your hardware. So some initial results we got then were as follows. Some relatively slow scanning, but just to show that the resolution then is preserved in a reasonable way. So high resolution at modest rates, hundreds of hertz. Then we went into the kilohertz regime, and we did a 3D example here of some battery material around a 30 micron cubed reconstruction. That took 3 hours to collect. However, the actual exposure time was only 15 minutes because you've also got now this larger overhead of the rotation stage. And so we began to play with removing these overhead of the rotation stage and collecting all our data in a single scan, a single hardware motion for all 4 axes. And we were able to achieve something very similar then in only 45 minutes now. Still not 15 minutes, but a big step forward. And that allows us now to start to image these smaller samples at quite a high repetition rate. So 45 minutes for a full volume can get you 25 volumes in around 18 hours. So in one day, you can do a whole energy scan, so you get a Zanes. And then in a whole beam time, in a few days, you can record several of these and get a whole state of charge measurement within one beam time. So we're really starting now to change what's possible on the science side by delivering these fast detectors to the beamline. Now the other side of the coin is larger volumes. So one thing is to repeat a measurement on a small sample many times. Another is to image larger and larger volumes to give you better statistics across your field of view. One example of this is bioimaging. And here's an example with actually a phantom brain. So this is a polymer which is designed to mimic the white tissue in the brain. And it's used often in MRI to model the MRI based models. And so we're very interested to image these structures at around 100 meter resolution across larger and larger fields of view. We're able to do that now, so we just did a 500 projection scan across 150 micron field of view in only 7 hours, and that gets you to almost 40 cubic microns per second. Okay, so this is a transformational from where we were just a few years ago, where we were waiting for every step for this motor to settle. Okay. Now, that's all well and good, of course. But what's next? Here's the Eiger. We maxed the Eiger out now. We've gone to 3 kilohertz continuous, 9 kilohertz in burst mode. But where can we go next? And the answer is, of course, the Selun. That's pretty obvious now, I think. And so DECTRIS got on board and came to work with us for a couple of experiments where we tested then what we could achieve with this same system if we could actually trigger much faster. And so the first demonstration of this was with a 2D sample, with a seamless star again, and we use our same flexible system now to trigger out at 110 kilohertz onto the detector, leaving not very many counts per frame, just a handful. But still, we proved that with the triggering system and the reconstruction algorithms, you could now achieve flux-limited resolutions across these fields of views. The trick here we played was to step very small, so we're only stepping 7 nanometers because the motion was not sufficient to move anywhere in the time of a Selun frame. Sorry. And so that leads us to the next thing. How can we now make this more usable? We can trigger 110 kilohertz, but how can we really use it? And that's the limitations. So one of the results that we found was even if we were scanning at 28 kilohertz or 91 kilohertz, we had more or less the same parameters coming out. So each scan was taking half a second because the motion was limiting us, so we couldn't actually traverse the sample any quicker. That led us to 800 microns squared per second, so impressive, but we couldn't go any faster. And the resolution was limited by the flux, because the photon counts is the same in the same time, and so we're photon limited as well. So motion and flux. Now, flux we'll come on to later, but motion we can improve slightly. So we got an upgraded motion controller, which could now trigger out at 4 kilohertz. We increased also the position capture rates to 16 kilohertz by just reducing some of the things that were being saved and optimizing slightly. And we also optimized the step size now. Because the motion controller could can have a tighter fit on this. We managed to jump from 7 nanometer step size to 250 nanometer step size, which allowed us to take more reasonable data rather than just overkilling the detector for the sake of it. Okay, and that allowed us then to get to a regime where we could actually save data continuously onto hard drives through a laptop. Hopefully at some point this will get integrated into the file system, but for now just to show that the data rates, although they sound big, actually in the end they are handleable by a laptop on a hard drive, and that's how we were collecting data that you'll see in a second. So, results, hot off the Beamline, these were taken just a few weeks ago, so no fancy processing I'm afraid, but you see the idea. 2D image now of 250 microns, ideally squared. There's a slight overhead. So actually it's 250 microns by 200 microns, but the resolution we believe is around 100 nanometers already. We achieved an improvement in resolution by going to pink beam slightly. So we're using now a full harmonic rather than just 10 to the minus 4 from a monochromator. And so increasing the flux and optimizing on the scanning, we were able to now collect 250 micron squared image in only 15 seconds. And to convert that into a tomography, you need 2,000 projections, and so we're able to do this in only 9 hours. So now we're over 300 cubic microns a second throughput in data collection with X-ray ptychography. I think it's pretty astounding for where we were just a few years ago. And to bring the whole thing back now to the smaller samples again and to the high throughput of smaller samples, and to really show off how fast you can go dynamically, I'd like to show you this example where we did 80 microns by 160 microns. We used a different stage, so rather than a 300 micron travel piezo, we used a 150 or 100 micron travel piezo, so much stiffer, smaller stage. That allowed us then to go even faster with the imaging rate, and we could collect this image in only 400 milliseconds. So we're really now getting to the point of matching full field imaging. The scanning is basically invisible at this point, okay? We're just completely flux limited in resolution. And still, we could then do 1,000 projections of this kind of sample in only 6 minutes. So now we're doing 6 minutes tychotomography data collection, okay? This is really going to start changing what you can do at the Beamline and really, really pushing to now in-operando, true in-operando measurements, these samples. And just to finish with a little bit of a raw detail of the beam time, you can see here how the stages were behaving. So this is a 6-minute window, or 5.5-minute window, and you can see how our motors, blue is X, I think red is Z, so they are interchanging as you're rotating. The orange line going across is a rotation angle. So you can really see how all these motors are synchronized triggering over the course of 5 minutes to cover your full 180-degree rotation. So the motors are working very hard. They're at the limit. But yeah, it's a lot of fun. So with that, I'll just get onto the outlook. Summarize slightly, Diamond is a third-generation light source. So all the images I'm showing here are with current technology, not with the Max 4 level of upgrades. But Diamond is pushing to that. So we are really much looking forward now to seeing how we can transfer where we are today with these flux levels using the technology provided by DECTRIS, for example, and our scanning system, combining these together, and I think it's a really exciting moment looking forward. So thank you very much for your attention, and
thank you very much. So
question for Sascha.
I'm sure there must be some questions, maybe. Yes. Let me see. I don't know where that's there. Ooh. Uh-oh. No, in this direction.
Thanks. Yeah, very impressive for this scanning and things. Just since you said at these flux levels, I was just wondering how many photons, say, per second are you recording on the detector? Or
So with the pink beam, I believe we were getting to 2 million-ish photons per pixel per second.
Sorry, how many?
2 million.
2 million per... so
per pixel per second.
I bet just sort of how many photons are coming onto your sample?
Okay. That's a different number. It must be around 10 to the 10, I would have thought, with the
10 to 10.
beam. Coherent elimination, something like
Okay, just to get a feel of, yeah,
that. Yeah, roughly, yeah. I can check it details.
thanks.
I also have a question. So I'm not sure, maybe I missed. So is this silicon-based detector?
This one was.
Yes. And can you go also to higher energies?
Yes, you can also go to higher energies. We have a high set sensor, and you can go up to 100 kV in the